When's our exam? Monday. Again, it'll be during lab. If any of you want to start sooner, let me know. I do not have anything because of the way my schedule works. That whole afternoon is free, so if you want to start early, just track me down, and I'll. I think in here is free. I just dump you in here. You can start early. And again, if you can't, let's say you have classes, but then you want to go later, I'll let you go later as well. Okay. So it's going to be the same format. I'm looking for quality. I don't really care about speed. At some point, you'll grow up and you'll start worrying about speed. But for the most part, I just worry about quality right now. Okay. With that said, also on Monday, I will open it up to any questions you have on the exam. But what do you have to have? You actually have to have real questions. So if you ask me real questions, okay, I'll give you real answers. If there are no real questions, we'll start the material. Okay. Questions on that? With that said, let's go on with what we're starting to do. What I want to do is, we found the V. So we said that V for a point charge. Morning, Joe. Is, okay, what did we say is?
Well, you taking a video?
Yes. Okay.
Hi.
That's fine. Got him?
Yes. It's exam day.
What did we say V is for a point charge? KQ over R. Now, before we had R, okay, before we had a voltage difference, and sometimes we have a difference here. Where did we say the difference is? We put our voltmeter here at V equals R, and where did we put the other lead? Do you get this expression? At infinity. Then we define the voltage at infinity to be zero. Okay. So this is V for a 1 point charge, and it's a scalar. So if I have something like this, let's say I have a whole bunch of charges like this. And if I want to find the V here, what might you do? What can I treat that object as? What's one of our standard tricks? As a collection of point charges. So what we can do, we can treat this the object as a collection of point charges. So then I'd have some little point charge here. I'll call this shaded in here. This would be my friend DQ. And D little q doesn't matter. And from here to here is R. So then I said the D, the tiny little voltage there is going to be what then? The point charge, we're going to have K dq over R. And if I want the total voltage at that point, what do I then have to do? Over this object here. So if I want the total voltage here, I'd have to integrate the dVs over here. So I'd basically have to do an integral over the object. Of this KdQ. And it turns out that we're going to do that. This is going to be a lot easier than finding the electric field this way, because I can do the same thing with the electric field. What's the problem with the electric field? It is a vector. So we had to worry about all those weird components. This is a scalar, so it's going to be a lot easier to work with. But what I want to show you today is why we even care, because it turns out that if you find the V at this point here, and this is what I'm going to prove, we will see today that the electric field at that point is given by minus the gradient of the voltage at that point. Where this right here, okay, remember how we defined it? We have to find out the other day. We did? Okay. X plus Y plus Okay, so this is an operator, meaning it has to act on something, and what this is, in this case, what it's gonna act on is this phi. Okay? And this is called the gradient operator. Okay, it's also sometimes called the del operator or the del operator. And the way you would refer to this, you would call this the gradient of V. That's how you would word that. And what I want to do is actually prove how that works. And what's nice about this is it's usually going to be fairly easy to find V, or easier to find V. And then you can just take the negative gradient and Shazam, you got yourself an electric field. Okay? Well, what I want to do is a proof of this. Proof. So hopefully you've seen, well, you probably haven't seen this part, Calc 3, but I'm going to state it. So what we're going to have here is that, let's do some background here. Let's say have a function of x, y, and z. In Calc 3, you're going to do what's called a differential. You're going to do this, you're going to do something called df. This is called the exact differential. Have you done an exact differential, Jack? Okay. So what is this going to be here? This is really going to be, this is really your total change in f. And so what would that be made up of? Well, the total change in f is going to be made up of any changes in f if you only change x, plus any changes in f if you only change y, plus any change in f if you only change z. So what this is going to be, this is going to be made up of basically the change in f if only change x, plus, and I'm still on the board, the change in f if we only change y, and plus the change in f if we only change z. Because again, this is going to be the total change here. So the question is, what is that going to be? This. So let's look at what is the change in f if we only change x. So in other words, x is going to go to some x plus dx. Let's figure this out. So I'll call this dfx. So this is the change in f if only x is changed. So in other words, I'm going to x to some point x plus dx. Okay, well, what that's going to be? That's going to be the partial of f with respect to x. Now tell me just in terms of words what that means. So what are you going to do with the y and the z and all the other variables? Treat them as a constant. So again, if you're to explain to like a little kid in kindergarten, explain what a derivative is. You say, oh, a derivative is how much something changes with respect to something else. So this is how much f changes if you only change x. Okay, so how much are we changing x by? From here to there, so that we're changing x by dx. So if I know how much f is changing if I only change x, the rate of change of f with respect to x. But then multiply this then by the change in x, that has to be how much f is changing if I only change x. That makes sense? So that'd be this from here. Well, tell me what this would be here. So in other words, I'm going to go from y to y plus dy. What would that be? Exactly. So this would be the rate of change of f if you only change y. That's the rate of change of f with respect to y, then we change it by this amount. And likewise for this. That would be this. Okay, for those of you who are engineers, at some point you're going to be taking a thermodynamics course. This exact differential is you're going to be doing this absolutely everywhere in your thermodynamics course. If you have no clue what to do in a thermodynamics course, take an exact differential. Even if it's wrong, your teacher will be impressed with the fact that you're taking an exact differential. And it's probably right anyways. That's the whole course is one big exact differential. So we put this all together. What do you get? So you're going to take this and this and this and put them in for here. So I'm going to say that this is, again, this is my total change in F here, because that's what it means to be an exact differential. It's going to be basically the partial of F with respect to X dx. So this is a change in F if I only play change X, plus the partial of F with respect to Y, change Y, plus the partial of F with respect to Z, and only change Z. That makes sense? Now, here's where the magic occurs. Some of the magic. This is an XY looking thing times an XY looking thing, plus a Y looking thing times a Y looking thing, plus a Z looking thing times a Z looking thing. Where do you have an X times an X thing, plus a Y times a Y thing, plus a Z times a Z thing? What kind of object? A dot product. So I can really rewrite this whole thing here as I hat partial of F with respect to X, plus J hat partial of F with respect to Y, plus K hat partial of F with respect to Z. I'm going to adopt this into basically dxi hat, dyj hat, plus dzk hat. And I go off the board. I have enough. And that makes sense, right? Because if I were to say take the dot product of this, you take this term, dot this term, and that would give you this. You take this term, dot this term, that would give me this term, dot this term, and that would give you this. Okay? Well, this is by definition, this whole thing here. This is by definition that gradient F. So we define that quantity there to be the gradient of F. And this right here, what would that be? Well, I'm changing X by a little amount, Y by a little amount, Z by a little amount. This is really going to be nothing but my half length DL. So what I have here is this. I can say that my total change here is going to be the gradient of this F dotted DL. Okay. Then I can integrate both sides here from some initial to final spot. So what would this be here? The integral of df is some F. I'm going to evaluate this at some initial to final spot. It's this guy here. So what is this? This is going to be F evaluated at some final spot. So some X final, Y final, Z final. Minus some initial spot. So this is going to be F at X initial, Y initial, Z initial. And that has to equal my buddy over here. Okay, what would this, do we have a name for that? If I have F evaluated at a whole bunch of final points, minus F and F and evaluate some initial points, does that have a name? No. That's your change in F. So what I have here is this. I'm going to change it F. It's equal to this guy here. Let's apply this to E and M. So apply this. to electrostatics. Okay, so we have, this is our thing here like this. Here's our E field. Here's my initial spot. Here's my final spot. Also, is this stuff on the test on Monday? No, this is all going to be on the second test. So we have this change in voltage here. And what did we say that change in voltage is? Well, keep going. How do we define it? We said it was a change in the electric potential energy over Q. We beat on this quite a bit and we got minus integral from some initial to final spot of E dot dl. We had that. Now, this voltage here, but that voltage here is a function of X, Y, and Z. Hey, suppose I want you to find the exact differential of F. I mean, exact differential of V. Do you have a way of doing that now? Yes, I do. That's right. You do have a way of doing that. How is it? Well, yes. So let's do it again. Okay. So how much does V change if I only change X? How did we write that? Partial. And V with respect to X dx. Okay. So this is how much V changes if I only change X. Plus, how much would V change if I only change Y? Partial V with respect to Y dy. Now, how much would V change? Again, this is your total change in V. So how much would V change if I only change the Z verb? Partial V with respect to Z, Z. Now, what did we say that looks like? An XZ thing times an XZ thing plus a Y thing times a Y thing plus a Z thing times a Z thing. A dot product. Okay. What is this a dot product of? It's the dot product of the I hat partial V with respect to X plus J hat. Ooh, that's a sad J. Partial V with respect to Y plus K hat partial V with respect to Z. What am I left over here? The XI hat, DYJ hat, DZ, K hat. Hey, what crazy name do we give this whole thing here? That is our definition of V. And this is going to be my little GL. What this tells me then is that the change in the voltage here is nothing but the gradient V dotted DL. Hey, let's integrate both sides from some initial spot to some final spot. Meaning from here. What does this side over here become? Yeah, that becomes our V at some final spot minus V at some initial spot. So that's our change in V. We're changing V, which is nothing but my friend over here. Okay. Let's put this all over here. What's this? Hey, but do we know anything else about the change in voltage? My friend over here. Okay. Now, what did we say about the electrostatic field? It is what kind of force? Conservative or non-conservative? Conservative meaning it is path independent. So it doesn't matter how I go from the initial to the final spot. I can pick any random path I want, and it always has to be the same. And in that condition here, this is always the same. What it means here is that this value here has to be this value here. So I can conclude that the gradient of V is equal to minus E for your electric field is minus the gradient of V. Boom. There are other arguments you can use, but I think that's probably the strongest one. Well, actually, the proof I just gave you was completely rigorous. That makes sense? So let's apply this actually to a simple case. And it'll even help you get ready for your test on Monday. And then you'll see how this all ties together. So let's apply this to a simple case. Okay, what kind of simple geometry do you have to treat, right? When you take your exam on Monday, you have to find the electric fields for various things. No surprise. You can use Gauss's law. And when would you use Gauss's law? Sphere, infinite plane, infinite cylinder. Okay. Let's say instead you had a finite wire. And I want the electric field here. How would you find the electric field for a finite wire length L? I ask you to find it here. What would you do? You treat this wire as a whole bunch of point charges. Okay? So let's do that case here. Let's actually take a finite wire, uniformly charged, and let's find the voltage here to do this. It'd be good practice for you. Okay, so let's do an example. Okay. Find the voltage at point P for a uniformly charged finite wire, wire of length L. Here's a wire, it has length L, like this. And I'm going to come out, here's some distance, here's my point P, and I'm going to call this distance here X. I want you to find V here. Okay. You are pros at this. You tell me how to do it now. Now, again, this is the exact same thing you have to do on your exam. The reasoning is going to be the same. The difference is it's going to be find E here. But those thought processes are identical. So this is actually exam prep. I think I have a room full of experts here. You tell me, room full of experts, how to proceed. Close. Okay, very, very close. Okay. What do I usually yell at when somebody shows me something? I say, I hand it back and say, I already don't like it. Usually what's missing? Okay, or make it more general, a picture of some form. So I want some picture in this form. So always go think about the fundamental physics. If I want you to find the voltage at this point here, what are you going to treat this wire as? A collection of point charges. So what would I want to see in a picture? I'd want to see a point charge in that picture. So we're going to treat this wire here treat the wire. As a collection. Point charge. So here I have, I'm going to give this a tiny little thickness, even though it doesn't have one, just to make it a little bit more obvious. I'm going to look at a tiny little point charge here like this. So here's a point charge. Give me the name for that point charge. DQ sounds like a great name. This would be DQ. Where is the R in this picture here? Where does the R always goes from where to where? From the point charge to the point where you want to find whatever you're finding. So the little R is going to go from here to there. This is R. So I can say that a tiny little voltage at this point here. What is a tiny little voltage then at that point due to my little friend DQ? What is the voltage for a point charge? K, Q in this case, DQ. It's going to be K dQ. On your exam on Monday, if I were to ask this for the electric field, what would you have? Instead, you'd have DE equals K dQ over R squared. Okay, but it's the same thought process. Now tell me what the technical problem is with that integral. Yeah, we're going to integrate this. I'm integrating on Q, but my R is varying. What was our solution out of this little dilemma? We introduced something. We introduced lambda, which is by definition charge per length. Okay, what's sigma? Charge, area, rho, the volume. Good. You're going to have our friend lambda. Lambda is by definition charge, length. Okay, you proceed. What is the charge for my little point charge? DQ. Over what width is that distributed? We introduced a new variable and we called it. Okay, we call it X prime, but you could call it all other things. I'm going to say X prime is going to go from the left end here to here. And call that X prime. So then the thickness of my little guy, that DQ is spread over what distance then? If this is X prime. Yeah, DX prime. So I'm going to say the thickness here, that tiny little thickness here like that, is DX prime. So this is DX prime. So my DQ, that's going to be lambda DX prime. So what does that mean about R? I'm going to have to write R in terms of X prime as well. So let's go through and do this. So from here to here is L. If this is X prime, again, this is really, really thick, tiny, so you don't even worry about the thickness. So this is L, and if this is X prime, what is that distance right here? This is L minus X prime. Well, if this is X, then R is here to here is
L minus X prime.
L minus X prime plus X. So what we have here is that this is going to be K lambda dx prime all over L minus X prime plus X. So this is now all in terms of X prime. Now we can integrate this. So now I can say that's a V here for the wire. It's going to be an integral. K lambda dx all over L minus X prime plus X. Now, where does the X prime go to from that picture? Again, I'm going to take the little DQs. And I'll take the little DQs and I'm going to add them up all the way along here like that. So if my little DQ starts here, the X prime is. And where does X prime go from? Goes from the left end to the little point charge. So if my little point charge starts here, the X prime is 0. Then I add them all the way up here. My little DQ here is my X prime is in L. So let's go from 0 to L. Okay, let's stop there. Does that make sense? That's a standard thing you'd have to be able to do on the exam. And if this had actually been the electric field one here, you'd have this exact same expression. What would be the only difference? What did you say the voltage, the electric field goes as AQ over R squared. So the only difference would be that this bottom here would be squared. That makes sense? Other than that, it's the exact same problem. Okay, so let's do that integral. To do the integral, I'm going to pull up a K and 11. Actually, I'm going to rewrite it like this. So what is that integral then? Yeah, it's going to be the ln of something. Right? If I just had that, dx prime over x prime, that looks like, that smells like an ln. So you would guess initially, K lambda, that there could be something in front. The ln of x plus L minus x prime, evaluated at 0 now. Now the question is there anything in front? So I turn to you. Is there anything in front? I'm hearing a -1. Agreed, disagree. Could there be a 4? How about a 4 pi? 2 pi cubed? 16 over 143. See, I think you're all smelling spring break. Okay. Spring break isn't until about 2 weeks away yet. So you can't be looking forward to spring break yet. I need your full attention. There's a minus sign here. Why does there have to be a minus sign here? Yeah, when you check it, what would you do? To take the derivative of a logarithm, you take the argument and you put it in the bottom. That's fine. I do agree with this. Then what goes in the top?
Derivative.
The derivative of this. Well, I take the derivative of this with respect to x prime, the derivative of x with respect to x prime is 0. L is a constant, that's 0. The derivative of minus x prime is -1, so I need the minus sign. Okay, so what would I do? I pull out the minus sign here. I put in the upper limit, I put in the L here. If I put in the L here, the L's cancel. This gives me the ln of x. Then minus, then if I put in the lower limit, in the 0 here, this is in the ln of x plus L. And I distribute through by the minus sign, and that would give me this. That would be V for the y. That makes sense? I hope there's a part B to this. Find E in the y. Okay, you tell me what to do. I could do the exact same thing and then just, put the square in here and carry it all out. That's all fine. Or I could use what we just learned. Why would I have you go through the whole calculation of finding V? Then I immediately ask you to find then E. Yeah, we can use the fact that the electric field is the negative gradient of your voltage. So what is this? This is going to be E. It's going to be your minus. Okay, this is the gradient operator is again this guy. Now friend V is right over here. Let's look at this. Let's look at the second term here. What is the y dependence in here? There is none. So if I take the partial with respect to y, what does that give me? If there's no y dependence. So S gives 0. Okay. Now let's do the derivative with respect to z. What is the z dependence on my body over here? 0. So the partial with respect to z, something that doesn't contain z, is 0. Hey, but does it contain x? Yes, it does. So what am I left with? I'm left with the electric field is minus I hat. Now, what would be, I just have the k lambda coming through. This is a constant here. So what is going to be the derivative of the ln of x plus L with respect to x? How do you take the derivative of a logarithm? People who are in Calc 3 or who have had it, who are engineering and physics majors, or math majors. Okay. The argument goes in the bottom. What goes in the top? The derivative of this with respect to x. So derivative of this with respect to x is what? I assume you meant the derivative of L with respect to x. Minus. Okay, what's in the derivative of the ln of x? Over x. And so let's get, I don't like any equation, so we have minus sign. So the way I'll write this is k lambda 1 over x. That's 1 over x plus L. I hat, boom. There she be. Quite slick. And this is exactly what we get if you did it the other way. So we now have 3 ways to find the electric field. 1, I can treat the object as a whole bunch of little point charges, find the electric field vector, and integrate over the object. That's one way. Another way is Gauss's law. Okay, Gauss's law is only true, so you can only easily use it in 3 cases. The brand new way is to treat the object as a collection of point charges, find the voltage at a point, and since it's a scalar, it's easier, and then come and take your negative gradient. So we now have 3 different ways to find the electric field. Okay? Now, you're going to have something else on test 1. What else do you think you're going to see on test 1? The binomial expansion. Let's do an example now where you're going to get the binomial expansion. Let's try another example. Let's say here's a plus q, minus q. Let's call this d over 2. Let's call this d over 2. Let's have a point P here, and this is Z here. And for part A, I want you to find B at P. Hey, does this little animal have a name if I have a plus Q and a minus Q? And it's a dipole moment. It's an electric dipole moment. Okay. So if I say find the voltage and my buddy here, P, due to these 2 things here, you tell me what to do. Close. Very close. And it's going to be V from the plus charge plus V of the minus charge. Why can I do that? Because the voltage is a what kind of object? The scalar object. You'd have to go to the scalar part of the zoo to find V. Okay, so we have 2 point charges. What's the voltage for a point charge? AQ over R. So tell me what the R is for my positive friend. So for my positive friend, I have KQ over. Now here's my R. And so this has to be Z minus G over 2. Now I have to add to that the V for my negative friend. So what is the V for my negative friend? Yeah, so I'm going to have a Z plus D over 2, because here's my R minus. K, I think there's one more thing. The charge is negative. So we have to have a minus Q there. Okay, so what we're left with is this KQ over Z minus D over 2 minus KQ over Z plus D over 2. Can't wait to find out what plug B is. Let's find out. What is V if Z is much greater than D? Okay, as soon as you're seeing the much greater, what are you thinking? Binomial expansion. So, this binomial expansion, again, what's the generic form of a binomial expansion? If you go to Wegmans, let's say you have a hot date on Friday night, can't find chocolate, so you're going to bring your date binomial expansion. Okay. Where in the Wegmans aisle would you look? I guess you could say, I honestly don't know. So, okay. You look at the 1 plus x to the n, where this x has to be
much greater, much less than 1.
much less than, or it was just less than 1. Then we're going to do the much less than 1. So you have to do that. So what do we have to do? We have to make this 1 over Z minus D over 2 and this 1 over Z plus D over 2. We have to make that look like this here. So we need to make 1 over Z minus D over 2 and 1 plus D over Z plus 2 look like 1 plus x to the n. What was our trick for doing that? Yeah, you have to pull out something here. So what am I going to pull out here at the bottom? You have two terms of D and the Z, and I always told you to pull out the larger term. That way what's left is going to be small. So in each of these cases here, we're going to pull out the Z. If I have this one here, you're going to pull out the Z. If I have this one here, I'm going to pull out the Z. Okay, if I pull out the Z in the top one, what am I left with? 1 minus D over 2Z. Does that make sense? So if we take this times this, that's my Z, and then this and times this, that's this one here. My bottom then becomes 1 plus D over 2Z. Now I give you a little rule of thumb. Where do you never do binomial expansion? In the denominator. So these little pieces here, what are we going to do? We're going to take them to the top. So you're going to write this as 1 over Z, 1 minus D over 2Z, the minus 1. This one's going to become 1 over Z, 1 plus D over 2Z. Like that. Okay, 1 over Z. What is the binomial expansion of this? What is X and what is N? X is almost, yeah, this whole thing here with the minus sign. This is my X. My N is my N. So what does this become? This becomes 1 plus N times my X minus D over 2Z. Why am I not going to worry about the plus dot dot dot? The next term goes as X squared. What do we know about X? Oh, okay. I was saying you're wording it a different way. It's gonna be much larger than the x squared term because your x is less than 1. If you take a value less than 1 and square it, it gets smaller. So these other terms are gonna be small. I can throw them out. Now the bottom term here, what happens? Left with 1 over z. What does this become? 1 plus, oh, this is to the minus 1. Sorry about that. I took this to the numerator, and I then put it to the minus 1 power. I apologize. So what do I get for that? Minus 1 times d over 2z. If I work this out, we get 1 over z here, and this guy. Minus and minus make a plus, so this is plus d. This z and this z makes it 2z squared. Whereas down here, if I multiply this out, I get 1 over z minus d over 2z squared. And this term goes in for this one, and then this term goes in for that one. If we do this, what am I left with? I'm left with z is this kq times this mess here. Then I'm left with the minus kq and that mess down here. Okay. What nice thing happens? Yeah, the 1 over z, the minus 1 over z here cancel. Then this term and this term then add. So this gives me 2kqd over 2z squared. The 2's go out. This gives me kqd over z squared. That's my v for dipole. If I wanted the electric field for a dipole, what would I then do? This is a part C. Negative gradient V of this dipole. Okay, and we'll do that part probably on Tuesday, because again, on Monday, what should everyone have for me? Questions. Again, if there's no questions, it'll be resolved. Okay. If there are questions, I'll continue to answer them as long as they're there. Okay. And again, if they're not, then we start with this stuff. Have a great weekend.